Hello everyone, welcome to the code space. In this video, we are going to learn the block mechanisms to achieve synchronization among the processes. In the last OS classes, we have learned software mechanisms to achieve synchronization and some other hardware implementations to achieve the atomicity among the instructions, and we are successfully able to achieve synchronization. But the problem in the software and the hardware solutions were they were non-blocking. It means that if a process is not in a critical section but comes into the CPU for executing its task, it will be stopped by repeating the CPU cycles, by wasting the CPU cycles, which is actually decreasing the efficiency of the CPU. Like, for example, if we take this is the critical section and we have the entry section here, somewhat like this, and the exit section here. So, when a process is in the critical section, let's say P1 is in the critical section, then P2 will not enter into the critical section, and when this P1 process, the process which is in the critical section, which is executing its critical section, is preempted out of the CPU, and P2 gets the CPU allocation, then P2 just wastes the CPU cycles by just executing the statements like while. For example, if we take the log variable while log equals 1, we'll just simply waste the CPU cycles when it comes to the execution of the process which is not executing the critical section. So the problem statement was to save this CPU time, like CPU execution to. So we came up with this block mechanisms. In this block mechanisms, if a process is executing this critical section, another process who is interested to execute the critical section comes into the picture, then the process P2 is completely blocked and sent into a sleeping queue. For example, in this case, the P2 will be sent into a sleeping queue, and once the process P1 completes its critical section, it exits from the exit section and wake up the process P2 to make in the to get the to remove the process P2 from the CP sleep queue to the ready queue, so that the process P2 can enter into the critical section now. So this is the main idea of these block mechanisms. Let's see the implementation. Like, block mechanisms are mainly implemented by two things. One is semaphores, and the other way to achieve these block mechanisms is by using monitors. So today we'll see the semaphores concept, what are semaphores and what are the types of semaphores, and how we'll achieve the synchronization using semaphores. First of all, semaphores are the abstract data types. What do you mean by abstract data types? Abstract data types are the data structures in which we can apply some operations. Like in this case, we'll apply the operation are down and the other one is up. We'll see about that first. These are the abstract data types on which we perform the operations like down and up with integer values, on which we apply down and up operations. Down operation simply implies reducing the value by 1, and up will actually increase the value of semaphore by 1, increasing by 1. Let's see the types of semaphores. Semaphores are mainly of two types. First one is counting semaphore, and the second one is binary semaphore. These are mainly differentiated by the values they take. The value of a semaphore in the case of counting semaphores can be any integer. Let me write any integer value. And in the case of binary semaphores, the value can be 0 or 1. The value can only be 0 or 1. Let's see the implementation of counting semaphores. So we'll take a structure counting semaphores CSEM type def struct type def struct. Let's say it as CSEM, in which it mainly consists of the semaphore value, which let's say int value, and the other one, this one is actually used to maintain the list of PCBs on which the down operation is unsuccessful. Here I have told you that will apply two operations. One is the up operation and another one is down operation. In the case of either the counting semaphore or the binary semaphore, there is no doubt that the up operation will fail. Up operation will be executed for every value of the semaphore. It is always successful, whereas the down operation can only be successful with some values of semaphores. We'll see while writing it down. And let's see the down operation first. Down operation will simply take a CSM, CSEM, and first of all, it will check, it will, since it is down operation and the type of semaphore is counting, it will reduce the value of semaphore, and if it will check if the value of semaphore reduces to negative, like it is becomes less than 0. If it is becomes less than 0, then it will put the PCB of the process into the sleeping queue, which is L in the above structure, and the process and sets the process to sleep. This sleep implies that the process is in the waiting state, and once the process is waked up, it will again get into the ready queue and get the chance of executing its critical section. Now, if the value of semaphore is less than 0, we'll put that process in the sleeping queue. If not, then we'll just simply return. This is the unsuccessful state of this down operations. And if the value of s is not less than 0, then it is said to be successful and it simply returns completes execution. Whereas the CSM, I mean up operation on CSEMS will increase the value of s dot value plus plus. And here if s dot value is less than or equal to 0, which implies that the value is came from the negative to positive, like or non-positive, mean non-negative, then it means that we can actually wake up a process from the sleeping queue and get it ready for the execution. So it selects a process from the sleeping queue, if any, and wakes up. This is the execution of up function, and there is no restriction or there is no condition of unsuccessful execution of up operation. So the main of this is written like this. First of all, we'll create a semaphore CSEM and we'll set the value of semaphore to 1. See, the initial value depends on the functionality or on the application. Let me discuss about that in just a minute. Then we'll apply the down operation. If the down operation is successful, then we'll go to the critical section and then we'll execute the up operation on that process. Now, let's see. Let's see the value of s dot value is 4. Then there can be a possibility of 4 processes executing, like entering into the entry section at a time, since the value of s is 4, we can consecutively apply 4 down operations without encountering any unsuccessful down operation, which means that 4 processes can actually enter into the critical section, which simply implies that mutual exclusion is not guaranteed. But if we initialize the value of s to 1, mutual exclusion is guaranteed. So in this way, we can achieve the synchronization by using the counting semaphores by setting the initial value to 1, first one. So now you may think that what is the point of maintaining the value an integer? Why don't we restrict the initial value to 1? But this can also be used for load balancing in the case of servers. Let's say we have a server which can handle a load of 1,000 requests per a second. Then we'll set the initial value of semaphore, like counting semaphore, to 1,000, which actually allows only 1,000 clients to get the access of the server. And if the count of these clients goes out of the range more than 1,000, then it will simply put that request in the waiting queue. So in this way, the counting semaphores are used to balance the load in the case of servers. So by the above conclusion, they come up with an idea of binary semaphores which can only take two values. Binary semaphores. These can be enough to achieve the synchronization. which only takes two values, 0, comma 1. These are enough to achieve the synchronization. In this, we just modified the down and up operations, like in the case of down operation on binary semaphore VSEM, we'll check the number of processes which are in the ready queue. Like if number of processes in the queue is less than, I mean, if the number of processes is not equal to 0, it means that there is a process in the sleep queue. First of all, in the down operation, we'll check the value of s. If the value of s is 0, which means that, like if the value of the s is 1, which means that one process can enter into the critical section and decreases the value of s by 1, which makes the value of s to 0, and then return. Otherwise, if the s dot value is not 0, which means that there is a process in the critical section. In that case, we just have to put this process in the ready queue, in the queue, in sleep. That's the down. And let's see about the up operation. Operation will also take a binary semaphore S and checks. Here it will check the size of the queue. Size of the queue. If the size of the queue is not equal to 0, it means there is some process in the sleep queue, then it will wake up that process. Otherwise, it just simply sets the value of S to S1, which simply implies that the critical section is completely free now, and any process which wants to enter into the critical section can simply enter into the critical section. So in this way, the binary semaphore is implemented. Now let's see the main code here. In this case, the binary semaphore. For this case, also the same. S dot value will initialize to 1 this time, and down of S will perform the down operation. And if it is successful, then we'll see the critical, like we'll enter into the critical section, and then we'll go to perform the up operation. Let's check for mutual exclusion. Let's say two processes which are ready to enter into the critical section, and the process P1 has entered into the critical section first, and the process when the process P2 and tries to enter into the critical section, it will check the value of S. When it tries to apply the down operation, the value of S is 0, which makes it into which places the process P2 into this sleep queue, which simply implies that mutual exclusion is guaranteed, as no two or more processes can enter into the critical section. Mutual exclusion is guaranteed. Let's check for the progress. If a process P1 and P2 are in the ready queue and the process P1 is interested to go into the critical section, but the process P2 is not interested in to go into the critical section, then there is no objection for the process 1 by the process 2 to enter into the critical section. The process 1 is independent on the interest of process P2, and it can simply, without any without any restriction, it can simply enter into the critical section and perform its own task, which simply implies that the progress is also guaranteed. Let us check for the important that and interesting condition, that is bounded waiting. Let's see the algorithm was successfully able to prevent a process from entering into the critical section again and again. Let's say a process P1 is interested into the critical section. So it performs the down operation with S initial value of S to 1. It changes the value of S to 0 and successfully able to perform the down operation. It executes its critical section and it will again go to the up, perform the up operation. And since the size of the queue is 0, it simply increases the value of S to 1. Now, in the other case, we'll have the process P2, which tries to enter into the critical section after P1, which actually makes the which P1 makes the value of S dot value to 0, which enables which stops the process P2 to enter into the critical section and puts this process P2 into the sleep queue. Now, once the process P1 completes its execution, it will check the size of the queue and wake up the process P2, and the process P2 is now shifted from the sleep queue to the ready queue. And then when the process P1 again tries to enter into the critical section, the value of S is still 0, which puts this process P1 in the sleep queue, which simply implies that bounded waiting is also guaranteed. Hence, this this is the solution for the synchronization. So in this way, we'll use semaphores to obtain synchronization among the processes. So I hope you get a clear idea on what our semaphores is, and you like this video and you get the clear idea and understood the concepts of the semaphores. In the next lecture, we'll see to achieve synchronization using monitors. If you like this video, please hit the like button and subscribe to our channel for upcoming content. Thank you for watching.